Have you ever really stopped to wonder how an AI learns? I mean, really gets it. It's not like it's just memorizing facts. No, it's this really fascinating, kind of chaotic process of trial and error. So today, we're going to pull back the curtain and demystify how we actually train a neural network.
Right, so this isn't science fiction anymore. What we're talking about is a brilliant mix of mathematics, a little bit of intuition, and a whole lot of trial and error that happens millions of times a second. Let's get into it.
So, what does it really mean to teach a machine? Well, you can forget about a classroom with desks and a chalkboard. It's way more like trying to tune a massive, incredibly complex instrument.
Okay, I want you to picture a giant control panel, and it's covered with millions, maybe even billions of tiny little knobs. Each one of those knobs, and in the biz, we call them parameters, changes the machine's final output just a tiny bit. The whole goal of training is to find the absolute perfect setting for every single one of those knobs so that the machine consistently gives us the right answer. The process itself, it's actually a pretty simple loop when you break it down. First, we show the network an example, let's say a picture of a clownfish. The network, with all its knobs set to some random starting position, takes a guess. Then, we measure how wrong that guess was. We call this the error or the loss. And finally, and this is really the magic part, we use that error to figure out exactly how to turn each of those millions of knobs just a little so it makes a better guess next time. And then you just do that again and again and again, millions of times over. But how does the network know which way to turn all those knobs? I mean, there are so many of them. For that, we need a map. And in the world of machine learning, that map is this beautiful, really complex idea called the loss landscape. I want you to picture a gigantic 3D terrain. It's got massive mountains, super deep valleys, rolling hills, the whole thing. Now, in this landscape, your elevation at any given spot represents how wrong the network is. The high peaks, that's where the knob settings are just terrible, leading to huge mistakes. But the deep, low valleys, that's where the settings are good and the answers are getting much more accurate. So, what's the goal of training? Simple. Find the absolute lowest point in this entire landscape. So how in the world do we navigate this thing? Well, the main strategy is called gradient descent. Imagine you're a hiker and you're blindfolded, standing somewhere on that terrain. You can't see the whole map, right? But what you can do is feel the slope of the ground right under your feet. So what's your next move? You take a small step in whatever direction feels the most steeply downhill. If you just keep doing that over and over, you'll eventually find your way down into a valley. And believe it or not, that's the core idea of how a neural network learns.
Sounds almost too simple, doesn't it? Just keep walking downhill. But as you can probably guess, in the real world, this journey is full of all kinds of treacherous obstacles. It's definitely not always a simple stroll down into the valley.
So here's our first huge problem. Modern AI is trained on absolutely enormous data sets. We're talking billions of images, trillions of words. Trying to calculate the true downhill slope of the entire loss landscape using all that data at once, it would be so incredibly slow, it's basically impossible. It's like trying to survey the entire Rocky Mountain range just so you can take one single step.
This creates a really interesting trade-off. We could use the entire data set, our whole map, to give our hiker the perfect, most accurate direction to step, but it would take forever. The alternative is to just use a small, random little sample of the data to get a quick guess of the downhill direction. This much faster method is called stochastic gradient descent, or SGD. It's like our hiker only gets to feel a tiny patch of ground before each step. Their path gets a little noisy, it zigzags a bit, but hey, over time, it still trends downhill.
All right, now let's talk about the terrain itself, because it's not always friendly. What happens if our hiker walks downhill and ends up in a small ditch? From their blindfolded perspective, every direction is uphill, so they think, yes, I found the bottom. But the true deepest valley, the global minimum, might be miles away. This is a classic trap called a local minimum, where a network finds a pretty good solution, but not the best one.
Another nasty obstacle is when the landscape just flattens out into a vast featureless swamp. Here, the slope is almost zero in every direction. Our hiker is stuck. They can't feel which way is downhill, so their steps become tiny and meaningless. This is the problem of vanishing gradients, and it's where the learning signal gets so weak that the network pretty much stops learning altogether. Progress just grinds to a halt.
And then you have the exact opposite problem, a sudden, terrifyingly steep cliff. When the slope is huge, the algorithm tells our hiker, take a massive step downhill. But that step is so big that it completely overshoots the valley at the bottom and launches them onto another mountain far, far away. This is called an exploding gradient. It leads to this chaotic, unstable training where the network's performance just swings wildly all over the place.
Luckily, researchers have come up with some essential gear for our hiker. There are techniques like momentum, which is kind of like giving the hiker a heavy backpack. They build up speed as they head downhill, and that inertia can help them roll right through those small ditches, those local minima. And then there's gradient clipping. You can think of this like a safety rope. It puts a hard limit on how big any single step can be, which stops the hiker from accidentally leaping off a cliff during an exploding gradient.
Okay, so we've got our map, we've got our blindfolded hiker, and they've got their gear. But how does this hiker actually calculate which way is downhill for millions of different directions all at once? We're still missing the engine that really powers this whole journey.
And this, right here, is the crucial point. Remember those millions of knobs? After we figure out how wrong our guess was, how do we efficiently figure out exactly how to turn every single one of them? If you had to calculate the effect of each knob one by one, it would be impossibly slow.
The answer is an algorithm that is, without a doubt, the cornerstone of all modern AI, backpropagation. At its heart, it's a remarkably clever calculus trick. Instead of doing things one by one, it starts with the final error and sends that error signal backwards through the entire network. As that signal travels back, it efficiently figures out how much each and every knob contributed to the final mistake, telling each one precisely which way to turn and by how much. This is the engine. This is what makes training these huge networks even possible.
And this brings us to the really big picture. Because this whole process, defining a problem, creating a network of knobs, and then using data and backpropagation to find the right settings, this isn't just some technical detail. It represents a completely different way of thinking about software itself.
The famous AI researcher Andrej Karpathy had a great name for this: Software 2.0. The old way, Software 1.0, was all about a programmer writing explicit line-by-line instructions for a computer. But with Software 2.0, you don't write the instructions. Instead, you create this huge space of possible programs. That's our network with all its knobs, and then you let the data and the optimization process find the best program for you within that space.
Let me put it another way. In Software 1.0, a human writes the code, and you get a fixed set of rules. In Software 2.0, the code is actually written by the data itself. The final product isn't a list of instructions. It's a finely tuned set of knobs, a model that has learned how to perform a task on its own. And what's really wild is that you can flip this whole process on its head. So instead of changing the network's knobs to get better at recognizing a cat, you can keep the network's knobs fixed and change the picture itself. You can basically ask the trained network, hey, show me what you think a cat looks like. And this is the core idea behind all that crazy generative art and the tools that let us, peer inside the mind of an AI.
So here's the big takeaway. We've gone from meticulously writing rules for computers to creating systems that learn the rules themselves just by navigating a vast landscape of possibilities. This has fundamentally changed what it even means to program a computer. And it leaves us with this one absolutely fascinating question. If code itself can be learned from data, what are the real limits to what we can build next?